constant this value per second. Even if it is not given, you can make out it is a first order reaction. 1.5 10 to the power minus 3. How long it will take for 5 gram to become 3 gram? So 5 gram to become 3 gram. So this is my R naught and this is my R. First order equation. Rate constant is given. We have to find time. The formula we know is K is 2.303 by T log of R naught by R. Very famous reaction, very famous equation for the first order equation, first order reaction. Plug in all the values. K is what given? 1.15 10 to the power minus 3 per second is equal to 2.303 by T. Log of R naught is 5 and R is 3. Both in grams, grams cancel. So if you solve this equation, you get T as 444 seconds. Log of 5 by 3 will actually come out to be 0.2219. Pretty easy question. The next is the time required to decompose SO2Cl2 to half of its initial concentration is 60 minutes. That is T half is 60 minutes. Because it is half of the initial concentration. If the decomposition is first order, it is given in this first order equation. Find the rate constant. Pretty easy question. T half is equal to 0.693 by K. Direct application of the formula for first order equation. This is only for first order equation. K is nothing but 0.693 by T half. And that is nothing but 0.693 by 3600 seconds. That is nothing but 10 to the power minus 4 seconds. If you don't know this formula, and if you know only the golden formula, that is K is nothing but 2.303 by T log of R naught by R, then also it's okay. So in this case, if you see the concentration is half, that means R becomes R naught by 2. So let's put R as to be R naught by 2 and T as 60. This is nothing but 2.303 by 60 log of R naught by 2. So if you solve this, this becomes actually log 2, correct? And log 2, and this becomes log 2 actually. You get the same value, right? This is 60 minutes. Convert into seconds, right? This was, so you'll get the same value. So if you don't remember this formula, it's okay. Just remember this golden formula. Calculate the half-life of the first order reaction for the rate constant given below. These are all my rate constant. This K. I have to find half-life. Pretty easy. It is a first order equation. I can just use the formula. T half is nothing but 0.693 by K. So I'll do it for the first. You can do it for the T half for first is nothing but 0.693 by K is 200 per second. You solve this, you get 3.47 second. Similarly for this you can do, this is for the first, per second. T half again 0.693 by T, T is 2 per minute. This is 0.35 minute. If you want, you can convert it to seconds. Similarly for years also pretty easy, same thing. We'll do it only, it's pretty easy. 0.693 by 4 per years. And that is nothing but 0.173 here. Right? Since we know it's first order equation, just use this simple formula and get the answer. Half-life of radioactive decay is 5730 years. Archaeology artifacts contain wood. This is an artifact which has wood, and this wood has only 80% of this C14 carbon that is found in the living tree. This living tree has some carbon, and then artifact which was calculated, there is some artifact or some monuments which they found, and this artifact has only 80% of this 14C carbon which is found in the living tree. We have to estimate the age of sample. Here order of the equation is not given, but we know it's a radioactive decay, and we know all the radioactive decay is first order equation. Since it is first order equation, we are talking about T half, right? Half life is given. We can find the value of K. So we know that K is nothing but 0.693 by T half for first order equation. I just showed you T half is nothing but 0.693 by K. So I can say K is nothing but 0.693 by T half for first order equation. That is nothing but 0.693, and T half is 5730 years, and that is nothing but 1.21 into 10 to the power minus 4 years. That is the value of K. So once I have found the value of K, I can find anything. Why? Because I know the formula, the golden formula. K is nothing but 2.303 by T log of R naught by R. Now in this formula, if you see, it is told that in this artifact is 80% of initial concentration. That means R is nothing but 80% of R naught. R naught is the initial concentration in the living tree, and this is in the artifact. So in artifact, and they are talking about the concentration of C14. So the concentration of C14 in artifact is R. Concentration of C14 in living tree is R naught. And it is told that concentration of C14 in artifact is 80% of concentration of C14 in living tree. That is, R is nothing but 80% of R naught. That is nothing but point R naught. So we'll use in this formula. K is we know, T we can easily find. So I can say T is nothing but 2.303 by K. Value of K we just found it, 1.21 10 to the power minus 4. This is per years. Per year, log of R naught by R. R is nothing but 0.8 R naught. R naught I don't cancel. So if you solve this equation, you get T as 1845 years. That means the age of the artifact is 1845 years. So with that, archaeology department finds the age of a old monument. And if you see here, this chemical kinetics is helping us to find the age of old monuments. The rate constant of first order reaction is given. Even if it is not mentioned first order reaction, we can just make out from the unit of the rate of constant, that is K. How much time it will take to reduce initial concentration to its 1/16th? That means I have some reactant to product. T is equal to 0, it was R naught. T is equal to some time, it becomes 1/16 R naught. I have to find the time T when it becomes 1/16th. This is R naught, this is R naught by 16. Since it is first order reaction, we use the same formula. T is 2.303 by K log of R naught by R. Actually, this K is equal to 2.303 by T log of R naught by R, but since I had to find T, I just told this formula. It's the same formula. Put all the values. K is 60 per second. Take care of units. R naught by R. R is nothing but R naught by 16. The final concentration. And R naught will be cancelled. This becomes log of 16. You solve this, you get 4.6 into 10 to the power minus 2. Unit will be second. And that is my answer. So this is the time when the concentration will become 1/16. That is 4.6 into 10 to the power minus 2 seconds. Very, very small amount of time. The concentration will become 1/16 of the initial value. Next question is, during a nuclear explosion, there is a nuclear explosion here. One of the products of 90 SR with half-life of 28.1 years, if 1 milligram of this 90 SR were absorbed by this newly born baby in the bones, instead of calcium, this 90 SR will absorb. The question is, how much of this will remain after 10 years and 60 years? 10 years is the adolescence time when this kid become adolescent, or 60 years when it's almost about to die. So the question is, if 1 milligram was absorbed, how much milligram will still be there, right, in the body? So half-life is given. So from half-life, the first thing we should do is we should find the value of k. Then only we can find all these values, right? How much it will be remaining. Let's find the value of k. So you know it's a first order reaction. Nuclear explosion is the first order reaction. So its T half is given, that is 28.1 years. Right? I know k is nothing but 0.693 by T half, that is 0.693 by T half, 28.1 years, and that is nothing but 0.02466 per year. That is the value of k. Very critical value. I got the value of k for this reaction. The next question is how much concentration of R naught, concentration of 90 SR will be there after 10 years, right? So the equation I know is k is 2.303 by 3 log of R naught by R. What is R naught? Initial concentration, that is in milligram. So this will also be in milligram. The final concentration is R naught is my initial concentration and R is my final concentration. And that is something we don't know. Let's put all the values in the formula. K is equal to given 0.02466 per year, 2.303 by T. In first case after 10 years. So let's put 10 years. Log of initial concentration 1 milligram by final concentration I don't know. Here get cancelled. You solve this, you get R as nothing but 0.7814 milligram. So after, even if 1 milligram was absorbed, almost 0.78 milligram will be there after 10 years also. Let's try to find for the value of 90 SR in this kit after 60 years, when is almost about to die in the old age. So here again let's put the same formula. K is 0.2466 per year is equal to 2.303 by T. Here is 60 year now. Log of initial concentration R naught 1 gram by final concentration. Here get cancelled. You solve this, here you get R as 0.2278. So if you see, even if when the person is about to die, almost 20% of what was consumed is still there, or what was absorbed is still there, right? So 1 milligram was absorbed. After 10 years, it is still there in the body as 0.78 milligram. After 60 years, when this person is very old, and when the kid becomes very old, it is still there 0.2278.